Okay, so we're going to continue our way through chapter 22. We're going to kind of scroll up here to see where we can find a good spot where we can launch into this. So here we go. Okay, so if you remember, kind of the theme of chapter 22 is once we generate these carbonyl compounds, which we talked about in the previous chapters, how can we start to use these carbonyl compounds to build larger molecules from them? And up at the top here, right, we talked about where the most acidic hydrogen is. We talked about those the alpha carbon there in yellow with those hydrogens, how we can put in a strong base. We talked about a couple of strong bases, sodium hydroxide, alkoxides, LDA. We talked about how and why you would choose one over the other. But if we deprotonate those yellow hydrogens there, we can form an enolate, right? And that enolate basically puts a negative charge on that alpha carbon, and then we can use that, I'm looking right here, we can use that negative charge on the alpha carbon to start to add things together. Okay, so that's kind of the name of the game for chapter 21. We're going to talk about additions to carbonyl compounds, but not additions directly to the carbonyl carbon, right? So additions, let's say, next door or down the street from, right? So go back and review your notes a little bit about how we were talking about these additions, just so that you're up to speed with what we're going to talk about here, right? So we talked about LDA, and how LDA can be used to couple some carbon compounds together. From there, we talked about condensation reactions. Well, sort of, well, we'll call them condensation reactions for now. How a ketone can react with another ketone, right, to form a species like this right here. And we're gonna pick that string up of reaction here in just a little bit, and what we can do with those. We talked about Claisen condensations, which is just how we can mix multiple ketones together, right? So Claisen condensations is kind of a name for this kind of idea right here. So if you want to look that up a little bit, and a different source to kind of follow along with how we can mix these things together. Right, so Claisen condensations, when we mix different carbonyls together. This is an important reaction right here, though, how we can form these diketones there, right? And this kind of all falls into this idea of a condensation reaction, right? Remember when we're talking about condensation, in this case, we're just talking about bringing multiple groups together. And we had ended in class with our alpha halogenation, right? So if we throw in something like, some base in the presence of bromine or chlorine or iodine even, right, we can add halogen to the alpha position. That alpha halogen there, I made the comment that alpha halogen, let's say, destabilizes the formation of another enolate, right? We do have another, let me grab a yellow here, right? We do have another hydrogen right there. And so it kind of, that hydrogen is acidic still, right? We could technically form another enolate, but that bromine or the halogen there kind of shuts that down usually. There is a weird case, or well, I shouldn't say weird. There is a special case, right, where if we have a ketone with a methyl group, right? So if we have a ketone with a methyl group here, and an excess of iodine and sodium hydroxide, we will go through this iodoform reaction, right? And we talked about how we will kick off the tetraiodo methane there. And the last thing we need to finish up with is, we're very rarely going to kick off just a negative charge there, right? And even if we do, it's going to be right next door to a formed carboxylic acid, right? So really, our answer for this is that we end up forming the carboxylate, which is important to recognize. We have our tetraiodo here, and then that just plucked that yellow hydrogen. Whoops, I didn't mean to write that. In yellow, right, we just plucked our green hydrogen from our carboxylic acid there. Now, the question might be, well, wait a minute. You just said that, this kind of shuts down, adding an iodo group there kind of shuts down our, subsequent iodination, all this kind of stuff. But this iodoform, so there's a couple of things going on typically, at least what we use this for in organic chemistry, is it is very selective towards ketones with methyl groups. Um, and I'm not saying it won't react with others, right? But what's interesting about this is we can basically chew off a carbon, right? So we can remove a single carbon with having that ketone with a methyl group next door. That's synthetically that could be useful, right? We've talked a lot about adding, right? Adding carbons together, but not too much about, chewing a carbon off. But a couple things going on, so why does this reaction work to begin with? Well, you're making a pretty darn stable negative charge here, right? So if you want to think about it in this way, right, you start out with a negative charge on a hydroxide and you end up trading that for a negative charge on a carboxylate. Now, carboxylate's a much more stable negative charge, right? So that's a good thing, right? And then the other thing that kind of happens is we typically run these in aqueous solutions or or aqueous mixtures of solvents. And iodoform here, right? Iodoform, remember, we're just chloroform, bromoform, iodoform, right? It precipitates out, right? So it precipitates out of solution. And you're like, okay, well, what's useful about that or what's important about that? Well, remember, as soon as something falls out of solution, right, it's not part of our equilibrium anymore, and it pushes the reaction to completion, right? So it precipitates out as a nice yellow solid, and so it's a visual indicator that there was a methyl ketone in our compound that we started with. And so typically this iodoform reaction is done when we're trying to identify an unknown compound in functional groups, right? You mix up an iodoform solution and you put it in there and you let it react. And if you see a yellow solid form, then it's an indication that you started out with a methyl ketone to begin with. But so that practical aspect aside, it is one of the not too many reactions that we talked about how we can selectively chew off a single carbon. So it can be useful in that sense also. So quick pause here, I'll be right back. Okay, so that's all we really wanted to talk about with the iodoform reaction there. But there was something important that's kind of we glossed over with all this previous information here. Not that we didn't talk about it, but I wanted to make an overt statement, right? So in all these cases that we talked about so far, we're generating a negative charge at that alpha carbon there. But there are two, right? In some cases, there can be up to 2 to 3 hydrogens at that alpha position. So what's stopping this from further reacting, right? What's stopping this from further reacting? Forming multiple enols, forming multiple enolates and continuing to do this chemistry? And the answer is nothing. In fact, that kind of tends to be a problem with enolates, is that they can continue to react. So even if we try to control stoichiometry and all this kind of stuff, they'll continue to react. And so how can we overcome this? And so with that idea in mind, let's talk a bit about Een Amines, right? So Een Amines. So Een Amines. And Een Amines are exactly what they sound like. They are amines where you have a double bond in there also, right? So something like this. Oops, I didn't give myself enough space here. So let's say we got this. Okay? So we got the ene part here, right? Our double bond, there's our ene part, and we got our amine part right up here, right? Fantastic. So an ene amine. Say, great, so what? Well, let's pause and think here for just a second, right? So if we take our enamine buddy here, right? Let's fill in our lone pairs. Let's push those down and push those up. And if we do this, right, what we end up making, let's give this, right, there's our nitrogen. That slams down a pi bond. We've got our other original sigma bond there. Right, and we end up with a negative charge on that, what we would call alpha position to the nitrogen there, right? And what can we do with a negative charge on a carbon? Well, we can do a lot. We can throw in we can throw in certain alkyl halides and benzyl halides and vinyl halides, benzyl halides and allylic halides to begin with, right? Some acyl halides, things like that, right? So we can react this enamine in a very similar way to what we do with the enolates. Now, the benefit of this is that this compound over here, right, is stable, right? We don't have to throw in a base or anything like that to start to generate this enolate equivalent here, the negative charge on the carbon there, as we did with a ketone or an aldehyde. This is just a resonance structure, right? Resonance structures exist to a certain percentage, whether we like it or not, right? That's just kind of the definition of a resonance structure. And so these enamines are let's say, a stable way to create a reactive alpha carbon, right? Now, a lot of this stuff, or at least the way the textbook kind of describes it, you're talking about Stork reactions, right? And that's just named after a certain chemist. I forget what his name is. Obviously, his last name was Stork, but he just kind of originated some of these ideas and was the first to kind of really publish some of the ideas with it here. Okay. So maybe I've convinced you at this point that enamines are useful, sort of, and you're like, well, I don't know, how useful are these things? Well, let's talk about how we can make an enamine first of all, right? So how could we make this guy here? Well, what I would need to do is take a ketone and add in an amine. And specifically, right, I need to add in an amine that has at least one hydrogen on it. Right? It can't have more than one hydrogen, and it has to have at least one hydrogen. So secondary amines, okay? Secondary amines. And we'll talk about why that is in just a second here, right? So if I mix these two together, and to make that happen, I need to give it a little H+, right? A little H+ action here. And if I mix those two together, then my product that I'm going to get out of this is exactly what we started out with, okay? That guy right there, okay? And you say, this seems familiar to something, and it does. If I take a ketone and I mix in a primary amine, so one R group, right? So an amine with two hydrogens on there, I would make this guy here a Schiff base, right, is what we would call it, right? I need a little H+ action in here also, right? And if you remember, we learned that a Schiff base is reversible, right? If we put it under some relatively harsh conditions, right? We can put some aqueous acid in there, some of that kind of stuff, right? It's reversible, and it'll get us back to our amine plus our ketone there, okay? Or we can protonate the amine and some water can come in and yada, 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 some of that kind of stuff, right? It's not easy to do, but we can do it, right? So we can remember, one of the topics I've talked to you guys about is, right, chemistry on paper is always easy, right? So it's pretty simple for us to do. And that's the same thing that's going to happen here also, right? This is a reversible reaction. It's a reversible reaction that we can put our enamine, right, our enamine, into aqueous acidic conditions, and we'll get back a ketone. And now, two things should pop up here, right? First of all, you should say, oh, well, that's really useful, right? Because the reactivity of an enamine is going to be different than the reactivity of a ketone, right? An enamine isn't really going to be all that susceptible to, strong reducing conditions, right? If you put LAH in there, it's not going to be as susceptible as a ketone will be. And so in a certain sense, you can think of an enamine as a protecting group, right? So if you see an enamine, there's a hidden ketone or aldehyde behind the scenes, right? Just as when we saw a Schiff base, right? This was a hidden ketone or aldehyde behind the scenes also. So it's reversible. That's important, right? These are reversibles. All right. And so we're going to we'll walk through the mechanism here real quick on how to form this. But an Een amine is formed with a secondary amine plus some acid and a ketone in there, right? So let's take a look at that mechanism. Boom, 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 boom. All right. Come on. There we go. Computer didn't want to cooperate with me. So we have some acid around. We'll use our generic H plus at the moment. Okay. Let's give a reason for this all to happen. So likely this is going to start out with the ketone getting protonated. Okay. Then our buddy, Mr. Amine, can come in. There's that. This would be a good time for you to pause if you want to and see if you can come up with this mechanism by yourself. You guys should be able to, right? I'm not going to show you guys anything drastically different than what we've seen in the past here. All right. All we're doing is essentially a nucleophilic attack on a carbonyl carbon, right? And it's a shocking change, I know. There's going to be some kind of proton transfer. So let's just do that there. Whoops, I forgot to put my positive charge there. All right, so let's just do that proton transfer there. Of course, we could bring in more of our acid or solvent in this case, might, shuttle some protons around. Not too important, right? Not too important in this case. So let's draw this here, right? We'll put a hydrogen, our green hydrogen that we started out with. Let's grab our red hydrogen here that we just transferred. Now we've got a positive charge there on our water. Excuse me, on something that can turn into water, I should say. We got this guy here. Right? So now we got it. Let's kick that water off. There it is. Okay. So at the end of this sequence here, right? At the end of this sequence here, double bond to nitrogen. And it's left with a positive charge, right? So we got that positive charge. So, right, it's a resonance stabilized positive charge, right? We can stabilize between that nitrogen and the former carbonyl carbon. Let's use yellow here, right? So if I just track that yellow carbon around, right, we can draw resonance structures to kind of stabilize that positive charge. But we want to make it, a stable intermediate, right? And obviously, we're going to make an Een amine. So let's finish this up then. Let's see what happens or what can happen. So I'm just bringing that same molecule down there. Since we were talking about yellow hydrogens earlier, let's just do that again. So something's going to come in. It's some kind of base. It could be water. It could be more amine. It could be another ketone. Something's going to come in. Grab one of these alpha hydrogens there and do this, right? So it looks very similar to a tautomerization almost, right? Or we're doing a proton transfer from an alpha, right, from an alpha position, right? There's that lone pair. We made a purple pi bond here, right? And we still have one of the yellow hydrogens there, right? So there we go. We have our Een amine, right? So our Een amine happens very similar to a shift base, right? Basically, a shift base would end here, right? With a deprotonation and a transfer of a hydrogen there. So, but if we don't do that, if we can't do that, I should say, then, right, we'll go on to make an Een amine. And right now, we know that Een amines are, they're useful for substitutions at the alpha position from a former ketone, right? Fantastic. All right, so let's take our Een amine here, and then let's do a couple quick examples of what we can do with it, right? So if I take Mr. Een amine, and if I put this in the presence of, let's say we put this in the presence of just generic Mr. Acyl Halide, right? Okay, so generic Mr. Acyl Halide. Well, whenever you guys see an Een Amine, right, this is where the magic's going to happen there, right? We're going to do this, right? Do this and do this, right? If we want to think about that kind of being the steps of what's going to happen. So let's see if we can follow along those arrows there, right? So we made right, so we left a negative charge here on there. We've got our buddy Mr. Chlorine right here, and we've got our methyl group here, right? So our CH3, right? Our CH3 there, right? Okay, we got that so far. Let me just make that very explicit, right? We got that negative charge on that oxygen. So as a shocking change of pace, right, we attacked a carbonyl carbon with a nucleophile, specifically that carbon that was alpha to our amine there. So kick pi bond up, pi bond comes back down and kicks off the best leaving group, okay? So this is what happens, right, at the moment, okay? So we kind of got that. And then we can come back and clean things up with some acid, H3O+, right? So we'll go back and we'll say, all right, now we need some H3O+. And so what the H3O+ is going to do is basically convert this guy here, right, back into our ketone. Fantastic. Now we've got a ketone next door to a ketone. That's pretty useful to do too, right? So we can continue to react some alpha carbons in this case, or do whatever we want to, and continue on with our synthesis, right? So acyl halides here, right? We can add those to Een Amines and add to the alpha carbons there, okay? These will also react, as I mentioned previously. Een Amines will react with vinyl halides. Excuse me, I said it again. Excuse me. Allylic, right? Allylic halides. Benzyl halides would react, right? Acyl halides would react, right? This is what we have to have somewhat reactive groups in there, right, to make this happen to any appreciable amount. Although, you know, there are many different conditions for this, right? We're just trying to give a brief example of what we have here in this case, right? So, all right, so I think this is a good place to kind of pause at the end here, right? This seems like a good chunk of information for you guys to kind of think through and work through, and I'll continue the lecture in the next video here also.